Math 2414, Taylor and Maclaurin series, video 13, multiplication of series. We only have 2 more videos to go. All right, so prior 2 videos ago, because the 1 video ago was optional, but 2 videos ago we saw a quick one about adding and subtracting series, which for the most part is pretty straightforward. In a nutshell, you combine like terms. Sometimes you have to dig to find them. But we can also multiply series, which sometimes is more handy than taking the direct approach. For example, if we were looking for a power series for f of x equals e to the x times sine of x, if we were to take the straightforward approach, we would need to be able to evaluate all the derivatives of this at 0. And the first derivative would require the product rule, and it's going to get uglier after that. Maybe not too ugly, maybe fairly manageable. And I challenge you to try to find an expression for the Maclaurin series for e to the x times sine of x. Excuse me. But we know both of these series individually. So can't we just use those results? And the answer is, of course we can. You just have to be careful, patient, and focused. So how would we do that? Well, let's go ahead and do it on the next page because I'm going to need the room. We know that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus et cetera, et cetera. Oh, and by the way, you may have noticed, although I didn't mention it, on the previous page in the instructions, that we're just going to list the first 4 terms of this power series. There's a reason why sometimes you just need a few terms at the beginning. It's usually because you're estimating something, and as your polynomial gets higher powers, you start getting smaller and smaller, and more decimal places that don't affect the accuracy too much. I didn't say that correctly, but anyway. We know the power series for e to the x, and we know the power series for sine of x. Sine of x starts with x, and then it's alternating and alternates through odd powers and factorials. Okay, so how do we find the product of these? Now, if you're thinking multiply like terms, stop that. That's the rule for adding. You can multiply anything. So how would we multiply this? Well, let's start by putting each one in a set of parentheses. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... Now, if you're worried about multiplying all these out, don't worry, we're not going to. We're just going to pick up the first 4 terms. And I was even inclined to pick up the first 5 terms. You know what? We will. Why? Why not? I may change my mind after we get to that 5th term. And I really don't need a 5th term out here, but I'm going to go ahead and write it. I'll tell you why I know I don't need a 5th term. Because when we multiply these out and get the first 5 terms of a power series, they are in increasing order of power, starting with 0 power. So there's a constant, then an x to the 1st, an x to the 3rd. How about constant, x to the 1st, x to the 2nd, x to the 3rd, x to the 4th. So for the first 5 terms, I'm going to have up to x to the 5th. So anything that's already greater than x to the 5th, I won't need. Because, for example, I don't need this guy if I'm only going up to x to the 5th. Why? When I multiply it times something over there, at the very least, it's going to stay x to the 7th, probably pick up a greater power. So if I only want the first 4 terms, yes, if I only want the first 5 terms, which go up to the 4th power, then I only have to worry about multiplying everything that's a 4th degree or below. All right, so how do you do this? This is like a superfoil problem. But the trick to doing this is just to focus on 1 power at a time, starting with the 0 power. In other words, the constants. The only way you can get a constant when you're multiplying two polynomials is to multiply one constant times another. Here's a constant over here, but there's no constant over here. So that 1, when I distribute it over there, is going to pick up some x's. So because there's no constant term in the second series, there's no way I'm going to get a constant term when I multiply these. So now let's move to x to the first power. To get x to the first power, I have to ask myself, how can I choose one term from each factor and multiply to get x to the first? Well, here's one pair, 1 times x. That will give me an x to the first term. Are there any others? The answer is no. To get an x to the first power, to get an x to the first power, we can only multiply up to a single x times a constant. And since there are no constants over here, then there's nothing I can multiply. Well, the only product I can multiply to get a first power is that one. There's no other pair of factors, one from the first parentheses, one from the second parentheses, that will give us a first degree term. So there's the only first degree. Now, let's find the second degree products. Let's start with this 1. What would I multiply by in the other factor to get an x squared? And the answer is I won't, because all these are odd powers. Multiplying it by 1 won't suddenly make it an even power. So we can't pick up an x squared from that factor. Can we pick up an x squared from this factor? Well, yes, if there's an x term in the other factor, and there is. Here's a product that will give us an x squared term. Is it the only pair that will give us an x squared? Oops. Well, let's move to the next term in the first factor, which is an x squared term. In order to multiply it by something in the other factor and keep it an x squared term, that would have to be a constant, but there are no constants over here. So x times x, this x times this x is the only product that will give us an x squared term. All right, let's move to the x cubed terms. For an x cubed, now I know why I wanted 4 terms instead of 5. Like, make up your mind, crazy man. Because the first term vanished, it's not there. There's no constant term. All right. So where were we? We did constant terms, of which there was none. We did first degree terms. We have one set up. We have a second degree term set up. Now let's look for third degree terms. We'll circle those in blue. Is there anything in the second parentheses that I can multiply by 1 that will end up with an x cubed? And the answer is yes. It's this. 1 times negative x cubed over 3 factorial. That will give us an x cubed term. But are there others? For example, can I multiply this times a term over here and end up with x cubed? No, because it would need to be an x squared term, and there are no x squared terms over there. But don't give up. Is there anything I can multiply x squared over 2 factorial by from the second parentheses that will give us an x cubed? And the answer is yes, this x. So we located another x cubed term from x squared over 2 factorial times x. Are there any other x cubed terms? X cubed terms? Let's find out by moving to the next term in the first parentheses. That is an x cubed term, but it's got to get multiplied by something over here. And since there are no constant terms in the second factor, whatever I multiply by is going to bump the power up. The smallest one is this, and that would give us an x to the 4th term. So we have successfully located all of the x cubed terms. And in general, when you're locating a certain degree term, you'll either be able to locate it 0, once, or twice. Hold on, folks. You'll only be able to locate it 0, once, or twice. And that was totally not true. So forget I even said that. All right, so where are we now? these are our, I've lost track of where we are. This is our first degree terms. This is our second degree terms. These two are our third degree terms. Now it's time for a fourth degree term. We'll do them in this color. So let's start with the 1. Is there anything on the second factor I can multiply to end up with x to the fourth? No. These are all odd powers. I'm only multiplying by 1. That's not going to change the parity of the power. And the word I just used was this. The parity of a number is its oddness or evenness. For example, the parity of 3 is odd. The parity of 4 is even. So we can't get an x to the fourth by multiplying by 1 because all of these have odd parity. Multiplying by 1 won't change that. Can we multiply by x to get an x to the fourth? Well, if we have an x cubed, and we do. So we have a fourth degree term that we get from multiplying x times negative x cubed over 3 factorial. But let's see if there are more. Let's go to the second degree term. Is there a term over here that would bring us up to fourth degree? No, it would need to be an x squared, but all of those terms are of odd parity. What about the x cubed over 3 factorial? Is there a term in the second factor that will bring that up to x to the fourth? Yes. We have plus x cubed over 3 factorial times x. And that is the last pair of terms that will give us a fourth degree term in our product. Now that we've located all the like terms for the first 4 terms in our answer, let's clean this up. 1 times x is x. X times x is x squared. All right, the next one's a little bit messier because I got some things I got to combine. Let's just take these up to the side and work them out. This is negative x cubed over 6 plus this is x cubed over 2. We can get a common denominator by multiplying this by some 3's. So I have negative x cubed plus 3x cubed, which is 2x cubed, and that reduces to 1/3 x cubed. Plus 1/3 x cubed. And then finally, the one in brownish color, if you will, which starts with this, which will be negative x to the fourth over 6. 3 factorial is equal to 6, plus this, which is positive x to the fourth over 6. Oh my, these cancel. Huh. I didn't find the first 4 terms of the product because the fourth one disappeared. 0x to the fourth over 6. Don't write that though, it's equal to 0. So if I really want to get the 4 terms, then I need to go out to 5th degree. Okay. Didn't see that coming. So we'll erase this guy that disappeared, literally. And let's see if we can track down all of our 5th degree. We'll put these in red again. So for our 5th degree polynomials, 5th degree terms, let's start with the 1. Is there a factor, is there a term in the second one that can give us x to the 5th? Yep, that guy. 1 times x to the 5th over 5 factorial is x to the 5th over 5 factorial. Are there more? Well, let's just keep moving up the terms. The second term in the first factor is x. To get x to the 5th, I would need to multiply that by an x to the 4th. There is no x to the 4th over here. So we'll move to the next guy. X squared over 2 factorial. If I want to bring that up to x to the 5th, I need to multiply it by an x cubed, and here's the x cubed term. So that gives us, let's see, that gives us, well, let's multiply it out. positive times negative is negative. X squared times x cubed is x to the 5th as expected. And on the bottom, we have 2 factorial times 3 factorial, which is not 6 factorial, and it's not 5 factorial. It's not a convenient formula for just multiplying 2 factorials. But is that the only 5th power term? Let's see. To get a 5th power term out of the next term in the first factor, I would need an x squared over here. There is not one, so I can't make a 5th power term there. But if I go to this next term, x to the 4th over 4 factorial, there is a term on the right side, x, that will bring it up to a 5th degree. So x to the 4th over 4 factorial times x is x to the 5th over 5 factorial. And that will be the last one because we just went backwards and hit the first term in the second factor. So let's see what all this adds up to. There's no x to the 4th term, but there is an x to the 5th. 5 factorial is 120. So we end up with x to the 5th, and I'm going to factor out the x to the 5th and put that in a better color. We'll factor out the x to the 5th, which will leave us 1 over 5 factorial, which is 1 over 120, minus 1 over 2 factorial times 3 factorial. 2 factorial is 2, 3 factorial is 6, 2 times 6 is 12. And then plus, what's 1 over 120 again? Common denominator is 120, so let's just do this. And we end up getting negative 8 over 120. And we can reduce that by 8 and get negative 1 over, let's see, 120 is 15. So the coefficient of x to the 5th is negative 1/15. So really multiplying 2 and the plus dot dot dot, there's more that we're not calculating. So really multiplying 2 power series together is just a matter of housekeeping and staying organized. Where's all the products that can get me a constant, get me x to the 1st, get me x to the 2nd, x to the 3rd, is however far you want to take it. So yeah, multiplying power series, a little bit annoying. There is a way to organize it a little bit better. Just going to show you real quick. I'm not going to redo the whole problem. But one way to organize it a little bit better is to actually make a multiplication table. And then write the terms of each polynomial, infinite series. For example, for e to the x, it is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. So this is e to the x. And for sine of x, that's just x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus et cetera, et cetera. Then you can just treat it like a multiplication table and maybe not complete it all, but complete it as necessary. For example, the constant term, there were no constant terms, but the 1st degree term would come from x times 1, which is that. We could actually multiply it all out. We get x squared. So now I'm multiplying everything by x cubed over 3 factorial, x to the 4th over 3 factorial. Excuse me, that one on the top is supposed to be 2. X to the 5th over 4 factorial. You just have to be real careful. Negative x to the 4th over 3 factorial. Then it starts getting a little interesting. Negative x to the 5th over 2 factorial times 3 factorial. Negative x to the 6th over 3 factorial times 3 factorial. And again, I didn't push it that far. I'm just completing the table. Negative x to the 7th over 4 factorial, 3 factorial, and so on and so forth. And then you can see all the terms and just gather the like ones. So as you can tell, multiplying is a little bit more cumbersome, but manageable if you stay focused.